Okay, chapter 16.6 deals with polyprotic acids, and we've actually covered most of what 16.6 has to talk about. Polyprotic acids are acids that can donate one or more, can donate more than one proton in acid-base reactions. Some examples of those are H2SO4, which can donate one proton to become HSO4 minus, and then donate a second proton to become sulfate ion, SO42 minus. And so all I want to add here is the idea that for polyprotic acids, we actually already talked about how each stage has its own acid strength, and how the first proton is the one that donates most readily, and that the successive protons are going to be weaker and weaker in their acid strength. Well, now we can just add the notion of Ka values. And so if you look at table 16.3 of your textbook, you'll see a number of polyprotic acids, and there will be a Ka1, that's for the first proton, a Ka2, that's for the second proton, and sometimes a Ka3. So let's just put all of this into practice. Let's suppose we have a 0.5 formal solution of ascorbic acid. And ascorbic acid has the formula of H2, C6, H6O6. Okay, and ascorbic acid has two hydrogens listed at the front of its formula, so that's an indication to you that this is a diprotic acid. And I'm going to go ahead and write their Ka values up here. So Ka1, sorry, give me a sec. Oh, shoot. I hit the wrong button. There we are. Okay, so Ka1 for ascorbic acid is 8.0 times 10 to the negative 5th. And Ka2 is going to be 1.6 times 10 to the negative 12th. 10 to the negative 12th. And you can see how it has become weaker on the second acid donation than on the first. Well, if I wanted to know the pH of this solution, I could also find the concentration of all three forms of ascorbic acid. How can I solve that when we really have kind of like two different equilibrium reactions occurring simultaneously? Let me write them up there. H2, C6, H6O6. And just to save board space, I'm going to, this will be one time where I use the H plus H, C6, H6O6 minus. So that is one of the equilibria. And then this H, C6, H6O6 has its own equilibrium where it donates that second proton. And we're left with C6, H6, O6, 2 minus. Well, what we can do is solve ice tables for both of these. And solving simultaneous equilibria can be really complicated, but we're going to show how in this case, in the case of polyprotic acids, it's actually not difficult at all. So we're going to have the initial change and the equilibrium. We'll do both of these ice tables side by side. And we start with 0.5. And 0 and 0. Have minus x plus x plus x. 0.5 minus x, oops, x, and x. So let's solve this one to start with. We know that 8.0 times 10 to the negative 5th is going to equal x squared over 0.5 minus x. And as usual, we will assume that that x is small. We can check that assumption after the fact, but I'm pretty confident that that will be a valid assumption. So we'll turn on the IPython console here. Here we go. And give me a moment here. Okay. And so we want to take the square root of that Ka1, 8 times 10 to the negative 5th, times the initial concentration of 0.5. And I get a value of x. X is equal to 0.00632. And it looks like that's going to be about just over 1% of our initial concentration, 0.5. I won't do the math because we know that that is going to be sufficiently small. Okay, so now we can put some values in here for x. 0.00632 molar, 0.00632 molar, and this is going to be now 0.494 molar. And now we can move on to our second equilibrium. Now this HC6H6O6 minus, we already have a concentration for that, 0.00632 molar. And H plus will also borrow from this ice table right here, 0.00632 molar. And we'll have 0 of that. And so we have minus x plus x plus x. And here we have x. Here we have 0.00632 plus x. And here we have 0.00632 minus x. Now this looks maybe like it's more complicated, but let's show you how it actually simplifies much more easily than the other one. We won't even need a calculator to solve this. Ka2, 1.6 times 10 to the negative 12th, is going to equal 0.00632 plus x times x in the numerator, and 0.00632 minus x in the denominator. Now if we assume that the x's here are small, then we can ignore them. And those cancel out. And x here is just equal to 1.6 times 10 to the negative 12th. It's as easy as that. So I can put x here as 1.6 times 10 to the negative 12th. And that's not going to affect these concentrations at all. 10 to the negative 12th is a teeny tiny number compared to all of these other numbers. And so now we're done. We have the ascorbic acid concentration. We have the HC6H6O6 minus concentration. And we have the C6H6O2 minus concentration. And finally we have the H plus concentration. Let's just quickly turn that into a pH. Oops. We're going to take the negative base 10 log of 0.006324555. That'll be more than enough sig figs. And I get 2.20 pH with 2.20 limited to 2 sig figs because of our Ka values. Now what we've done here is simplification. It's a little trick. We've done our math as if this is a first step and then this is a second step that doesn't go back and affect anything from the first step. When in reality both of these are happening simultaneously, and you could imagine if this change value were large enough to go back and affect things here, well, we would need to account for that. But in practical terms, for multiprotic acids, this second step is always negligibly small. The only reason we needed to do this second step at all was to figure out the amount of that C6H6O6 2-. It did not affect our other concentrations because this number is so very small. And so it's a way that makes these problems much, much easier, but it is perfectly valid. So that's all I have to say about polyprotic acids.